I guess we can start. Yep. Okay. Thank you very much for coming for another iteration of BHI Colloquium. Today, we are very glad to have Spyros Alexakis from University of Toronto, and he's going to tell us about singularity formation in black hole interiors.
Okay, thank you very much. Thank you to everybody for the invitation. I've been for a conference here a couple of years ago, and I really enjoyed it. So thank you for the opportunity again. So I was a bit unsure what to speak about, what topic. So I chose the most conservative one that definitely is about black holes. The only small caveat is more it's about the interior of black holes. So let me start by discussing some things which I think are well known to most of you. So maybe I'll present them from a slightly different angle at the beginning, and then we'll get to recent results. Okay, so let's start with the first example of a black hole very briefly. So it was discovered by Oppenheimer and Snyder. And I'd like to give you the description of this black hole from a more geometric point of view. So as I suppose we all know, Oppenheimer and Snyder were motivated by the question, what is the analog of the collapse of a pressureless fluid in Newtonian gravity? Okay. So Newtonian gravity, a fluid with zero pressure will attract itself by gravity. And given that there's no pressure to push back, it will collapse, all the mass will collapse to a point. So the question was, what happens with this in gravity? So let me maybe describe the picture geometrically with snapshots of time. Let's think of the space-time metric as an evolving metric in time, and I'm going to take snapshots of the space-like part of space-like slices. So the initial condition of Oppenheimer and Snyder was a portion of a Schwarzschild exterior, so which contains vacuum, which joins up with the support of the fluid. And the support of the fluid is on a spherical cap. So this is a region inside S3. In fact, initially it is less than half of S3. So it's a portion of a spherical cap. And it's a unique spherical cap so that if you choose your portion of Schwarzschild with R greater than 2m, it's the unique sphere that joins up with it in a C11 way. So the metric matches and the first derivatives of the metric match. So this is the initial data for Oppenheimer and Snyder. So the red is the support of a fluid, blue is vacuum, blue is Schwarzschild. It's the portion of Schwarzschild. Oops, I'm sorry. Okay.
You're just stepping on the cable.
Oh, I'm sorry.
No,
Okay. So
the presentation.
Yeah.
It's a you know. Okay. Let me use the board now. In the meantime, I will need it eventually.
Okay, it just needs to be plugged back in over there.
Okay.
I think it just unplugs.
You just go ahead.
I'll go ahead. Okay. So in the evolving, at the next snapshot I want to focus on, in the Oppenheimer-Snyder, the fluid has contracted. So, and it covers a hemisphere, exactly a hemisphere, which joins up with Schwarzschild at R equals to m, R greater or equal to 2m. And then something interesting happens, which to describe it, let me rotate, do a coordinate change by 90 degrees. So let's rotate by 90 degrees. So at the next snapshot, the metric can be described as follows. It consists of a hemisphere at the very end, which joins up with a cylinder. So the hemisphere is still smaller. Okay. The density of the fluid has increased. And it joins up with an S2 cross interval, which eventually opens up. Okay. The next. And let's say this is T1, and let's go to time equals epsilon. What occurs in the evolution is that the cylinder becomes very, very thin in its S2 direction and very long in the remaining direction. And the spherical cap at the very end matches up. Okay. So the spherical directions behave like epsilon. The cylindrical direction blows up like epsilon to the -1/2. And eventually there is an opening up very far away, but I'm not certain. And at time equals 0, there's a collapse. So the cylinder has fully contracted in the two spherical directions. It has infinite expanse in the remaining direction, and the sphere has, the hemisphere has disappeared. Okay. This is Oppenheimer-Snyder from a geometric point of view, viewing snapshots. So I've drawn this. Oh, well, I had drawn this here. All right. So our interest for today is how stable is this behavior here of this collapsing system. That's my question for today. Okay. So, so the proper understanding in many ways of the Oppenheimer-Snyder was through the Schwarzschild solution understood by Kruskal. So to connect a little bit with a picture, for the double-ended Schwarzschild initial data consists of two copies of the Schwarzschild we all know, right, which join along the neck. So this would be the initial data. And the evolution then has a region inside the black hole with this Penrose diagram, with a final terminal singularity, a space-like singularity, which corresponds to this blue, this collapsing cylinder, but just of infinite extent if you take a suitable gauge, suitable coordinate system. Okay. So these are the first two examples of black hole interiors. And so let's discuss the nature of the singularity. It contains an infinite contraction in 2 dimensions and an infinite expansion of the 3rd dimension. Okay. And again, the question is, how stable is this? So the immediate answer is not stable at all. Okay. And you can see this by the example of a Kerr solution. So the Kerr solution, as we all know, bifurcates off of Schwarzschild. You can perturb Schwarzschild by adding a tiny amount of angular momentum, and you have a Kerr solution. And so whereas Oppenheimer-Snyder has this Penrose diagram, it's a one-derivative solution with a singularity, which is space-like everywhere. And Schwarzschild has this Penrose diagram. The Kerr, when you introduce a tiny bit of angular momentum, the behavior changes dramatically. So the singularity had been here. Right? The singularity immediately disappears. And you can continue the solution up to some boundary. The maximal hyperbolic development gives a boundary, the Cauchy horizon, where the metric extends up to the Cauchy horizon smoothly, even real and live. One could continue the metric, in other words, past the continuum of the Cauchy horizon. People often do that, but we're interested in only the maximal hyperbolic development, so let me stop here. So I want to stress the complete instability of the space-like singularity. It was here, but then the tiniest perturbation of initial data leads it to it disappear, and the solution can continue very nicely for a very long time.
So it's not that the coordinate singularities you can continue it. It's just unstable.
Yes, this was a real singularity. Thank you for stressing it. This was completely, the Schwarzschild singularity is a real singularity. The curvature blows up. Okay, but so it is unstable. So let me take a point here and take a geodesic that goes towards the singularity. Let's say it had length 1. I can take the same point here, the perturbed metric, and shoot up to time 1, and nothing will go bad. In fact, I continue up to time 2, all the way up to time 2, and the metric remains smooth. The curvature remains bounded. So it's a complete instability.
Now, you encounter boundary at some point?
Yes. So in the explicit Kerr solution, there is a boundary, but it's a Cauchy horizon. So this is a smooth. This is not. There's no singularity here. The metric extends smoothly up to this boundary. In suitable coordinates, you extend smoothly up to this boundary. And you could construct any extension. You could construct lots of extensions past this, which smoothly solve the Einstein equations past this. Okay. So let me digress a bit and discuss singularities in cosmological setting, which in principle is something completely different, but we'll find there actually. Okay, so this goes back to the 1920s. So the most well-known is the Robertson-Walker singularities, which discussed isotropic and isotropic fluids. So all directions are the same. And imposing this ansatz, we want to put so one can construct explicit solutions that we all learned in a basic GR course, where all directions shrink down to nothing. So Q is the positive constant. We go up to time equals 0, and the whole space has shrunk down to nothing in a synchronous gauge in the GD system. A more involved solution is the Kastner solution from 1921, which is only in vacuum. So here there was fluids of different possible equations of state. Here there's vacuum. And these are explicit solutions found by Kastner, which are of this super explicit form. Right? So the metric is T3 or R3, whatever you prefer. And you've got three separate exponents, which are forced by the Einstein equation to satisfy these two equations. Okay? So you will note by elementary first grade math, one of the two numbers must be negative, possibly zero. Okay? If the sum of the squares is 1 and the sum of the numbers is 1, one must be negative. Okay? Which means that there must be one direction of expansion. Okay? So in these explicit solutions, one must have in the direction of expansion. All right. Okay. So let's do a further generalization of Kastner. Kastner had the special case that it had homogeneity. Okay, so 3 killing fields. But implicitly, we said it's T3. So implicitly, the 3 killing fields all commuted. One can seek to generalize this to say, I want homogeneous spacetime, so I want them to admit 3 killing fields, but they need not commute. And a general form for this metric would be of this form, where the components would depend only on time. So there would be these 1-1 forms, or matrices, if you like, which see the 3 killing fields. So the metric on each slice, on each time slice, is a Lie group. It contains these 3 killing fields, and one can classify the Lie groups according to the Lie algebra structure or the commutation pattern of the 3 basic killing fields. Okay. So this has been done over 100 years ago by Bianchi. Okay, there are 2 classes A and B in dimension 3. Let me just, for this review, let me just discuss class A. So the most simple setting is where all of them commute, and then we have to be at least locally Kastner. So the metric is got as Kastner. And the commutation pattern is the most complicated, where let's say absolutely nothing commutes, and all the Lie bracket components have full possible rank. So these are types 8 and 9. So some 2 tensor has full rank. These are the Bianchi types 8 and 9. And one could consider the Einstein equations as any of these Bianchi types. This has been done. And so let's just say, in some sense, if you are restricted to the class of homogeneous solutions, the most general type is when you have absolutely no commutation of any kind. Okay? So all the 2 tensor that comes into class A has full rank, and in some sense that's the most generic to consider. Okay, and in that case, so in that case, one expects that the behavior of the solution has some oscillatory mixed master behavior. So when time is going to 0, you don't converge to anything. This has been predicted by Berlinski, Khalatko, and Lifshitz, started from the 1960s. There's some rigorous mathematical work on this by Hans Rinken from 2001 onwards. Let me describe this prediction at least briefly. So actually, I'll return to it in a bit. So one expects some chaotic behavior bouncing between different Kastner states at each, right? So at each point, this is a homogeneous spacetime. The evolution is bouncing between different Kastner states according to, in the limit, according to an explicit law, an explicit hyperbolic linear.
Spyros?
Yes.
When you have mixed master behavior, do you necessarily know that it ends in a singularity, or is it possible for it to avoid that somehow?
Okay, so let's say generically it does end in a singularity because generically the curvature blows up. Okay, there's a genericity statement about, right? So I want to avoid that, but generically the curvature blows up.
Okay.
In the cosmological setting, it's predicted. Okay, it's predicted. There's very little explicit proof of this.
Okay.
Right. So Ringstrom has some explicit.
Basically, if I were looking for a statement about genericity of geodesic incompleteness in the business solutions to a given, let's say, vacuum gravity.
Yes.
I can talk about open sets, but this is going to tell me some fraction of the, some measure on the space, so I could tell, okay, more than half of the solutions, more than half the base space.
Okay, so what this would do, I think, and I'm speaking a bit from, so in this super specific class where you've got 3 killing fields, right? So it's not generic at all, but within this class, I think generically you could say there will be.
Right, but I want to talk about like type, say, just a generic class, like jump at 8 or 9.
Yes.
Is there anything that's known about how frequently you get actual geodesic incompleteness?
I think Richard has shown this. I'm speaking a little bit from memory, but I think this follows from Richard. I mean, Bianchi class 9.
Okay.
Yeah, in this class in Bianchi. 2001, the paper I covered in my class last year. Okay, so let's go back to, so for the time being, the cosmological setting was an aside. We'll see it joins up, but for now, let's go back to black hole interiors. So motivated in part by the examples of Schwarzschild and Kerr, maybe the cosmological setting, Penrose conjectured the following. So, so consider an initial data set with reasonable matter models. Then the maximal hyperbolic development inside a black hole, once you have a black hole, will end at a terminal singularity. So terminal means is not completely defined. It means that the Einstein equations cannot be continued past the singularity in any reasonable sense. You can't say I can find an extension past the singularity, which continues to solve the Einstein equations in some reasonable sense, even in a weak sense. Let's take this. This was Penrose's definition. And my understanding was, when this was done, if we think back to Schwarzschild and Kerr, you might think there are more Kerrs than Schwarzschild, right? So Schwarzschild is a special class within Kerr. And Schwarz is the one that has a singularity, whereas in Kerr, there's no terminal singularity. So the motivation for this was mostly the desire to say that general relativity is a deterministic theory. Because if you could terminate at the horizon past which you could construct many extensions, which one will you choose? So it was based on that, and if you like, he was putting emphasis on this desire that it's a deterministic theory, so it must terminate at a real singularity, a terminal singularity. Okay, so the nature of what the singularity should look like, how the metric behaves upon approach to the singularity, is left open. There's a strengthened version of this, also due to Penrose. So let me call it now the strengthened strong cosmic centrism, which would say generically the singularity should be of space-like type. I haven't quite defined what this means, but let's say space-like type. And it should involve collapse in all spatial directions. Collapse in spatial directions, not in all, but in some spatial directions there should be collapse. Okay, so space-like, to give a, would mean, let's think of the differential structure. Let's just think of the manifold before thinking of the metric. And what it means is that different observers going to different points on the final surface along time-length trajectories cannot communicate. So light signals, if we go sufficiently close to singularity, light signals emitted by one observer cannot be received by the other observer. That's a fixed light. Okay, so this is strengthened strong cosmic centrism. Okay. And collapse should mean what? We've already seen in Schwarzschild, some directions can collapse, the other ones cannot. So let's take it in the sense of the area element. Okay? So the area element associated to a time like geodesic congruence, the area element should be going to 0. Okay, so a little fun digression. So this is, it was widely believed, and so here's let me take 30 seconds of our time. So there was a quiz on the centenary of the Einstein equation by the BBC. Okay, and there was one question that I got wrong. So let me confess here. Okay, so how much you know about black holes? When a star collapses into a black hole, all the mass gets squeezed into what? So I thought the event horizon, right? But no, the correct answer according to the BBC is a singularity. So the BBC, number one, it believes there's a singularity, but also note it seems to espouse the strong, right? Because it's squeezed. Okay, the squeeze suggests that there's a contraction. Okay, so the BBC believes in the strong cosmic centrism.
Well, also I have to say that there are black holes without singularity in them.
That's right. So okay, so we've disproven the BBC. Okay, all right. So okay, so let's go back a slight bit to the cosmological setting, and let me try to connect them actually. So the prediction for cosmological singularities, for initial Big Bang singularities, by Belinsky, Alexakis, and Lifshitz is that generically, and that is very important to stress, generically, a vacuum spacetime without any homogeneity, nothing, a generic statement about a set of all possible initial data will oscillate wildly prior to the singularities. And the dynamics of the space-time at each point upon approach the space-like singularity across a time like geodesic, the metric will oscillate, but its oscillation approaches a billiard, specific hyperbolic billiard between the circle of Kastner parameters in that. Okay. So this has been around and it's been built on and made explicit. In fact, there's a very good book by Belinsky and Benoit from just 2 or 3 years back that describes this and provide arguments in favor. Okay, so was initially made for the Big Bang singularity, but one can extrapolate this to black hole interiors. Okay. And the reason is because of the space-like nature. If you believe that singularity is space-like, then the metric doesn't know if it's entirely close to a black hole or close to an initial singularity. The Einstein equations are time reversible. I mean, in space-like, you don't know what's happening. If you start with initial data very close to singularity, you don't know where you were. You don't know if there was a black hole. You don't know if you were close to the initial singularity. So there's an extrapolation for black hole interiors. Okay.
If we're talking about the Big Bang, isn't it hard to say what generic initial data is because
Yes. So
it's at the Big Bang?
that's right. So you could say if I go epsilon time after, and I consider the space of initial data and solve backwards. So treat it as an initial value problem.
Manifestly identical to the.
That's manifested identical to this. That's right. So one can question if that's a valid interpretation of Big Bang generic, and surely it is. For black holes, you can say that is the correct. If you're interested in black holes, then this interpretation start with initial data very close and consider the space of possible initial data there. So one could interpret generic. Okay. So
Sorry, in the sense of for Big Bang, I guess I'm confused. If you have a Big Bang in a flat universe, there isn't a sense in which you have well-behaved initial data, right?
flat universe. Sorry.
Yeah, like a singularity followed by scry, but scry ends because of the Big Bang singularity. So it's not, there isn't a sense in which you have a generic or any kind of initial data slice that's smooth everywhere.
You could go time after. Yes. Okay. Fine. So
Well, I mean, you
I
don't
think
have an I0, right? You don't have an I0 in that.
So you're talking about a cosmological constant or the?
No, flat. Like when we have just, the usual, you have a scry,
Yes.
but which is not complete, and then a Big Bang singularity.
Yes.
Then
But
any
what-
initial
but
data
it-
space has to like touch the singularity at some point.
It depends how you think of it as an initial value.
Uh-huh.
If you want to think of it as an initial value. If you want to think that there was a time 0 and I'm just solving backwards, this makes sense. This notion of generic makes sense. I think
Okay.
what you're saying is for Big Bang, I don't want to think that way.
Yeah, that's what I'm saying. Yeah.
Fine. So don't, and then this
Yeah,
is not
sure.
valid. You can't apply what I'm saying.
Yeah.
Okay. So let me discuss, for example, the Linsky and all recent book. So the argument in favor is for the physics. Okay, so let me just give a very descriptive summary of the argument. So it uses the Hamiltonian formulation of Einstein equations. It stipulates that there's a space-like foliation, right, by affines.
So if you're in this reverse problem, is it generically true that it will expand out to something which is smooth?
You're saying so if you solve backwards, maybe there is a singularity. But if you solve forwards, what happens is that
Yeah.
so that's widely not known at all.
That's probably.
Yes. But that's the large data problem for Einstein's equations,
Yeah.
which we don't know. It's pretty good.
So we might think that the initial conditions are very, very special.
Yes.
Generic. It's very different to apply the genericity argument to the initial data,
Yes.
as opposed to the final data.
Sure. So if you want to parameterize data by the final data, suppose you had long time existence and some sort of limit of time equivalent data. Yes, so you can ask the parameterization at initial time. How does it map to the parameterization at final time? Is that map reversible? Is that
Oh,
where you're going?
That's not what I was asking. I mean, it doesn't really make sense to say. it seems the problem is very different, right? Things happen, it goes on and starts to collapse and it's.
Sure.
But, it doesn't make, I don't know what it means to talk about generic, it gets back to the problem what generic
Yes.
initial data is at a singularity.
Yes.
Even if you do what you said, which is take generic initial data, epsilon after the singularity,
Yes.
that won't evolve into a generically, we don't expect it to evolve to some smooth.
Presumably not, yeah, it depends on the equations. Right,
Might or might not.
right. Presumably black holes will form, yeah, sure.
Yeah.
Let me say from my
It's
lecture,
physically a very weird.
so generically for me, for this lecture, generically for this lecture, we mean in terms of an initial data problem. So, right? So the question of if you wanted to prescribe data at the singularity, what is the space of allowable data? What would genericity mean there? Is a very, very different question. There'll be a tiny, I'll present one result from that, but not mine, but one. There'll be some result about prescribing data at the singularity, but that, for me, the data does not mean at the singularity, it means somewhere before. Is it? Okay. Okay, so a little bit back to the BKL argument. So they use the Hamiltonian formulation, and so the Hamiltonian is broken into many pieces, of which, if you believe that you're close to a certain caster, it's clear that near every caster, some parts of the Hamiltonian are important and drive the evolution, or some are very, very small. Okay, that's their argument. And they predict, so somehow they drop the terms that you believe are small, they say they're zero, and they predict that the dynamics are fully driven by the dominant terms of the Hamiltonian. Okay, so the key driver of the oscillatory behavior, of the bounces, the key driver of that is a non-integrability of the diagonalizing frame of the second fundamental form. So when you're going down to one point, you can look at each, you can consider the second fundamental form, right, the momentum, if you like, and you can look at the frame that diagonalizes. Okay? If you compare that from point to point on the space-like slice, that changes. Okay? The diagonalizing frame changes. So the key driver is the non-integrability of that principal frame. Okay? That's what drives the dynamics. Okay. Within this prediction by BKL, there is a certain special situation, okay, which they identify. And they call it the asymptotically velocity term dominated behavior. So what this means is that in a suitable coordinate system, in the energy, if we think of the derivatives of the metric, or the entries of the energy, all the energy goes to the time, it all becomes kinetic in the limit. Okay? So it means that the spatial derivatives of the metric become insignificant compared to the time derivative of the metric. Okay? So all the energy goes to the kinetic. Okay? So this is a special situation which they identify within their broader picture. If this happens, they call it AVTD, asymptotically velocity term dominated. Okay, it means that the velocity component of the derivative dominates the spatial components, but the energy becomes only kinetic. Okay? And if that were to happen, then at each point on the final singularity, you converge to a Casimir. At each separate point, you converge to a different Casimir. So different means that the Casimir exponents at each point are different. So it's a different Casimir at each point, but also the frame, okay, the principal frame, that changes from point to point, the principal direction.
So just to clarify, one of those principal directions is the expanding direction. Is that right?
Yes, yes, that's right, yes.
And so that can be in one direction and the next point may
It's
have
another direction, that's right, yeah.
I see, okay.
That's right, exactly. So, okay, so concretely would mean that the metric would look like this, right? So you have a splitting. If you can take a GD-SIG gauge, a time parameter like this, the metric would have a splitting, so everything is contained in these components. Okay, and so if you are in ABTD, it would mean that at each point there's a stabilizing orthonormal frame in the limit when time goes to zero. And so the second fundamental form behaves like this. There's some Casimir exponents depending on your point, and it will look like delta ij times the corresponding pi, right? the order t to the -1, and the correction, the remainder, is strictly better. And again, at each point, you're going to a cascade. So this is what AB to D would mean. Okay, so let me start with some results on this. To rigorously prove chaotic behavior is way farther than what present mathematical techniques suggest you can try. There have been results for, in fact, quite a long time of constructing examples that behave the ABTD behavior. So let me describe that. The first results, so it's come out of our conversation, the first results I haven't even put down. The first results are, let's impose data on the singularity, and let's try to solve away from it. You could do it in a black hole, so it's at the terminal singularity, you're solving backwards in time. You could do it at the Big Bang, so of initial data and so forwards in time. The earlier results, and these are maybe 2 or 3 decades old, and I haven't put them down, I haven't even put the names, are what's the class of data? It's analytic class. Okay, so essentially, it's you're requiring your data to be real analytic in a certain sense. So you get your solution, you get existence of your solution by Cauchy-Coalescence. Okay, there are many results like that. So what you do is you produce lots of solutions which have ABTD asymptotics when you go to the singularity, because you went to the singularity prescribed data and you solve for a short time. Okay. So analytically, it relies on this very classical
Singularity of point rather than a Cauchy surface. How do you put data?
Okay, so
It means
it's like prescribing a metric which is becoming singular. So in some directions it is collapsing, in some directions it's expanding. It's like you take a function times t. Yeah, it's like you're prescribing the powers. Okay, so t to the minus something times a number, t to the plus something times a number. So it's a renormalized, if you like, sense of data. The more rigorous result was done by Fournot and Luck in 2020, and where their seed data is not analytic, it is, in a sense, in a Sobolev space, okay, which is what modern day analysis works with. Okay, so they prescribe seed data at the singularity, and they impose a certain integrability of the principal frames. This integrability is what turns off the chaotic dynamics. So they say, I'm going to put it at the singularity, I'm going to impose it there. And what you mean by integrability? It means that the Lie brackets of the two collapsing frames, two collapsing directions take the Lie bracket, it has no component of the expansion frame. So in specific, a specific component of the Lie bracket would be 0. So they go to the singularity and they say, I'm going to prescribe data there and I'm going to set this parameter to 0. Okay. And if I can do that, if I assume that, then I can solve. Then I can solve for some positive time. Okay. So this is the one result in terms of predicting, imposing data at the singularity. Okay. I'm trying to communicate with physicists here. So in some sense, some degrees of freedom are set to 0. You set it by hand to 0.
Is that equivalent to saying that the expanding axis
Yes.
is the same at neighboring
Yes.
parallel?
That's right.
Okay. But these guys can do whatever.
The two can commute, but their commutation needs to be in their own span, so not in the expanding one.
Okay.
But the span can move, twist around as you move in the.
It can twist around. Yes, it can twist around. So there's a further restriction, which will be my result in a second. So just hold on. Okay. So that's okay. So that was one for Big Bang. Let me say another sequence of results by Rodniansky spec initial, and then for not Rodniansky spec. So again, for Big Bang, there are high dimensional results where they prescribe data after the Big Bang and want to solve backwards. And where they're in a certain regime that they call subcritical, where BKL predicts that you're going to have ABTD behavior, they derive it. So so in higher dimensions, there exists a regime where you don't need any of this Lie brackets to be 0. In very high dimensions, there is a regime where generically in a certain range of parameters, you should have ABTD no matter what, in an open set of data in higher dimensions. So the first results were that. And they obtained the optimal such result in 2020 together with Fournot, and also in dimension 3, they showed that if you have a certain polarization condition, then in dimension 3, then you will have ABTD again. You're not going to have. And you know that the curvature blows up at this specific rate, so it's definitely the real singularity, C2 set. The curvature is blown up. Okay. Let's now go to black holes. And, so one result is by the Firmus and Luck from 2017 and onwards. So they're saying that for generic perturbations of a Kerr solution, a portion of the singularity is weak null. So number one, it is not spacelike, it's null. And the portion is the one that emanates from time like infinity. So let's recall. So the Kerr solution itself had a Cauchy horizon. So what they're saying, let's take double-ended Kerr for now. So if you perturb your initial data here, then the Cauchy horizon will persist as a null surface, but the metric upon extension, upon approach to the Cauchy horizon, is no longer a smooth metric. So exactly how non-smooth, I think has not been yet determined, but at least it doesn't accept a continuous extension. Okay. Right. So there's some weak null singularity on a portion of the Cauchy horizon. After that portion, one doesn't know. Okay, but a portion of the singularity is weak null. So this particular shows that generic. So the statement that the entire singularity should be spacelike is false for black holes. But it doesn't describe the full singularity. It sees the portion that emanates from I plus. In a very concrete sense, this is coming from I plus. It's coming from
When you say weak, you mean the Christoffel symbols are still square angles?
I'm not, to be honest, I've forgotten exactly what they derive. Okay. So I'm not sure they've derived that yet. Okay, but definitely not.
This doesn't happen for Schwarzschild. It doesn't mean special.
Yeah, so this is you're perturbing a real curve with angular momentum.
That's what part of it comes to knowledge.
Yes, because the curve right now, you could say I perturb a Schwarzschild to introduce angular momentum. Okay, but then I'm closer to the curve of that angular momentum. This does not work if you perturb a Schwarzschild but retain angular momentum 0. Then this result does not apply.
Like, why does part of your part of the similarity become null?
Why? Yeah, I'm not sure I can answer why, but a way to think about it is the curve itself initially had a null horizon. So just that null horizon is still there. It just became somewhat non-smooth. That's one way to see it. Okay. So our challenge is what I was interested in is to understand what happens for perturbation of Schwarzschild. Okay. So we can go inside the black hole and take a hypersurface just before the singularity, perturb that, and try to understand, can I solve all the way up to the singularity? And what does the metric behave? How does it behave when I get to the singularity? Okay. So the obvious problem is you have to say that there's this counterexample right now. So you couldn't take any perturbation. You cannot. So somehow I have to exclude the possibility of going to a curve. Okay.
Are you working with pure gravity?
Yes, pure gravity, pure vacuum, yes. So okay. So let's see. So let me present the result. First, let me remind you the Schwarzschild solution that we all know. So we're going to be going to R equals 0. So my starting point is epsilon, and I want to get to R equals 0. So I'll take this data at R equals epsilon, I will perturb it. Okay, so let's recall, to introduce the perturbation take, let me remind you, Schwarzschild has many killing fields. Let's focus on d theta now. So d theta is a rotational killing field. So I will, okay. And the rotational killing field is polarized, which means that the d phi is normal to all the other directions. Okay, there's a splitting of the metric. There's no g phi t, no g phi theta, right? There's a splitting of the metric for Schwarzschild. So this condition is called the polarized axisymmetry. So you have a killing field with closed orbits, this one, and that's axisymmetric. And if it's normal to the remaining directions, that's called polarized. So that's the class in which I'll consider data. So I'll consider axisymmetric and polarized perturbations of the Schwarzschild data. Let's say at R equals m. So inside the black hole. Okay, then the solution will develop a space-like singularity, right? And which I can normalize, gauge normalize to occur at r equals 0, and the metric will look like this. So my gauge is to ensure that this term is the same as it is in Schwarzschild. So remember, in Schwarzschild, r is a time coordinate inside the black hole, so I've made the beating exponent exactly the same. Okay, and then there are collapsing and expanding behavior of the key components. So these exponents will remain close to what they were for the Schwarzschild. They'll be close to the values they had for Schwarzschild, but that the exact behavior depends on the point you're at on the singular surface. Okay. So the exponents here, the key exponent is the alpha exponent of the killing direction, right? And that determines the remaining exponents. Okay, so I have got 1 degree of freedom. One exponent tells me what the others are by solving an algebraic equation, something very simple. Okay, and the remaining one will also, so alpha will be close to 1 like it is in Schwarzschild, and beta will be close to 1 like it is in Schwarzschild, depending on alpha, and the remaining direction will expand like it does in Schwarzschild. The rate, the exponent will be close to the Schwarzschild. Okay. There are some cross terms, but they will be smaller, they matter less. Okay, so that's the main result. Okay. Okay, so I'd like to present some of the ideas. So it's quite a long work. I want to describe some of the ideas and more in big picture. And I want to emphasize some parts that I think are maybe useful for other people. So the one thing is something well known, I think, to many of the audience, but I want to present it from a different angle. So when you have axisymmetry, the Einstein equations, the vacuum Einstein equations reduce. So they become an equation in the 2+1 metric. And let me, so the Einstein equations for the 3+1 metric become this system for the metric in T fine theta in the 2+1 direction. Okay. So you can think of it as a free wave. And then the Ricci curvature in 2+1 is given by this explicit expression. Your initial reaction might be, this doesn't look particularly nicer than that one. Here Ricci was 0, here Ricci is something, and something falls away. Okay, so it doesn't look you found anything by doing this. But I want to emphasize in 2+1 dimensions, right? This equation, if you treat the right-hand side as given to you, becomes ODEs. And if we're trying ordinary differential equations, not partial differential equations, ordinary differential. And now understanding singularity formation for partial differential equations is usually very difficult. But for ordinary differential equations, it's better. It's much better. So let me emphasize, let me describe quickly how this goes. So the second set of equations in a certain frame, just in a parallel transported of a normal frame, becomes a set of ODEs. So let's recall the second fundamental form, right? For this, for a time-like congruence, we have the second fundamental form. And so what happens is we have the first equation on gamma, and the second equation is telling us the Ricci curvature of the 2+1 metric is some expression. We also have the standard Riccati equations that say the evolution of the second fundamental form is given by the curvature tensor. In any, this is a geometric equation. So in general, as we all know, the curvature tensor decomposes into a Weyl part and the Ricci part. Okay, so the Einstein equations have prescribed the Ricci part, but the Weyl is, you have to solve somehow. You're not given locally. In 2+1, the Weyl curvature is identically 0. That's why you obtain this ODE system, right, for the case. Okay? Normally in 3+1, there would have been a Weyl tensor that you don't have a local expression for. But here you're in this section. Okay? So let's pay. So in a certain sense, the wave is the driver for the ODEs, but the wave itself is solving a linear equation, right? It's a linear equation. It's a quasi-linear system. It's coupled because the metric on which the wave evolves is determined by the wave itself. Okay? But then this evolving metric satisfies ODEs driven by the wave. And so this is good for me because understanding how the metric will become singular is ultimately driven by the ODEs, and it's easier to do that. So I was trying to convey trying to convey this as an approach. This approach works in axial symmetry. You don't need to be polarized. It generalizes a bit, but it's.
You say they're ODEs?
Yes, but okay. If you take the gamma as given, then it's an ODE. Okay. And you're able, and you want to do an analysis where you want to think of the gamma as given. So maybe I'll get to that in just a bit. Okay. Okay. So maybe let me give a big picture of the argument. So you could do something non-mathematical, which is formal asymptotics. So suppose that the metric behaves like you believe it will behave, and then find formal asymptotics for solutions of the ODEs and the wave equation. That's not very difficult to do. And formally, it will depend like this. So it'll be an alpha, depending on the point t and theta, times log r. Okay? And this is what's giving you the collapse or expansion of the e to the gamma. Okay? All right. And then the principal directions, k11 and k22, will blow up according to these such rules. Okay? One has a negative sign because this sees expansion, and one will have a positive sign because it sees a contraction. So if you want to do some formal analysis, how you expect all the parameters to work, it's not too hard to figure it out, how it's going to go. This is not a mathematical proof, though. So let me show a little more. Okay. So one thing which is very, very essential to the analysis is that although we chose a geodesic frame, so we chose a congruence of time-lapse geodesics, we derive that the expansion for this congruence will have this universal law. The different components have different coefficients in front, but the trace will be to leading order fixed, constant. Okay? This would be, you would call this constant mean curvature in the math languages. Okay, so this is leading order, it's constant mean, asymptotically constant mean curvature. And you're getting it for free, right? So if you believe that this is what the asymptotics are, it so happens that independently of how the components, what values they have at each point, their sum will work out to all of P3 halves. Okay, so you're getting this asymptotically constant mean curvature for free. I've tried to stress that doing this splitting of the equations and treating them as ODEs is something which maybe one should try more broadly. Okay? In axial symmetry, you have this feature, and I think it's been somewhat underexploited. Let me now say some of the difficulties you face and how you kind of make it into a proof. Okay. So let me say that the difficulty from a geometric point of view. If you believe that you've got contraction in one of the directions and expansion of the other, and if you want to work with a congruence of geodesics, the contraction is very, very, very dangerous. Okay? Because we know in a general space-time which is absolutely smooth, right? A time-like geodesic, a congruence of time-like geodesics can form focal points. When you've got infinite contraction, it's super easy. If you take two generic, somehow a generic congruence of time-like geodesics, they will form focal points before you reach the singularity. So how are you going to do analysis? Right? So your parameters blow up before you reach the singularity, not because anything is not smooth, it's just a failure of the gauge. So this is very dangerous. The contracting direction is very dangerous. The expanding direction is good for you because if things are stretching out, then why should they form focal points? They're not going to. Okay. So because of this, we've got a method of proof which relies on an iteration. I'll describe it maybe very briefly. So, okay, so let's study the two equations. So the expanding component of K has a leading order behavior. If you believe that gamma is behaving the way we said, you can read off the leading order behavior. It won't blow up. It's got a favorable sign. The collapsing direction has an unfavorable sign. So if you believe that you can solve all the way up to the r equals 0, if you knew that, then you can read off the leading order coefficient. But you don't really know that. And now in analysis, you also have to differentiate. You have to look at derivatives because you're working in a Sobolev space. So the following feature happens. If you look at the evolution equation of the second of K22, of the collapsing K, it's a linear equation in the derivative. Right? This is a linear ODE. So you have a free branch. When you've got linear ODEs, you've got like the general solution has the following behavior. And this is enormous. This is absolutely awful. So if this actually happened, if this was reality, if your K had the feature that it blows up like r to the minus 3 halves, but its spatial derivative, maybe because of gigantic oscillations, really did blow up this much worse, you cannot prove. You cannot derive any estimate. You cannot prove anything. So your hope is that somehow this doesn't really occur. It's allowed by the solution. I mean, the general solution would allow such a branch, but the branch is not really there. That's your only hope. So we derive that this is the case. All right. So if this was the case, then if you're trying to do an iteration, at each step, the estimates will be getting worse and worse and worse by a gigantic power, and nothing will converge, and you don't derive anything, and you don't get a result.
Would this be a bit better if we were to start with ingoing null coordinates? And so, the focusing there is a bit better for one class of congruences.
Okay, so in mathematical GR, what gauge you choose is a very important choice. We don't do null coordinates. So it would be very difficult to I think that the collapsing would still work against you. The fact that the metric is squeezing down would say null coordinates will also tend to want to become, you'll get focal points before you reach. Okay? You could imagine that you'll solve this problem in null coordinates. I think for space-like singularities, I don't think the best choice. People haven't, in fact, for Nodavlos, Verniansky, and Speck have done it in CMC, and that's the more traditional way. The physics literature uses a time-like congruence. The more mathematical takes a constant mean curvature fluctuation. We took a time-like congruence. Okay, so let me just give you a big picture, and maybe let me not tire you so much. So the approach is by an iteration. So I'm solving a sequence of equations, which in the limit should converge to a real solution. So I've got some some hypersurface in coordinates where my initial data lives. I'm going to solve the wave towards the singularity, starting with this hypersurface, determined from the previous step. So at step M, I've got the previous metric, I've got the previous hypersurface, and I'm solving a new wave. That's a linear wave. It's always smooth. I can do it. Okay. And then I want to solve the Riccati equations for the two components backwards, because I want to ensure that I chose a congruence that doesn't have focal points, and I can start, if I start with the singularity, I can do this. And that free branch about the derivative of this, I can set to 0 if I start at the singularity. Okay? And now the difficult part of this was substantial novelty, I think, is you need to find the initial data surface. So you need to solve for the hypersurface where your initial data will be induced. Okay? So this is maybe more mathematically involved, but we need to do that. And once you've found the initial surface, then you put the remaining data on that surface, and you solve again forwards. And these are the branches that are in no danger of blowing up. Here the gauge is variable. So you set up an iteration of this way. We call it the forwards-backwards iteration. And you can show that in the limit, it will converge. You will get a solution. So it's an iterative way to solve the equation. One feature is you've taken all the nonlinearity as ordinary differential equations. That's good. That's helpful. Okay? But you pay a price because of the gauge you chose. You have to set it up forwards and backwards. All right. So that was the big picture view I wanted to give you. So maybe let me do a tiny bit of an outlook. So beyond space-like singularity, beyond everything, we've introduced an approach that works for classical gravity, 3+1 gravity, under axial symmetry. So the key feature is that the nonlinearity is encoded in ODEs, and the rest is wave equations, or if you take away polarized image, it's a wave map, but into a favorable value. Okay, so you get more control this way. Because you're working with ODEs, you get more control of the geometry. Usually in analysis, you get bounds and estimates, for how you convert that to asymptotics is not so easy. Here you get it immediately because it's ODEs. Okay, so my hope, and I'm trying to convince people of this, is that this becomes a method to study, to extend the many works in general relativity that have been done with 2 degrees of symmetry, usually with spherical symmetry. Okay? So you study the Einstein equation in this class, you can derive stronger information because the equations are more simple, more detailed information about black hole interiors, about many, many things. But of course, it's got 2 degrees of symmetry. You would want to say, you could say that everything you've done is because of this strong symmetry you've imposed. So we have a way here to move away, at least kill one of the degrees of symmetry, and lock more dynamics, allow more dynamics. So I'm trying to convince people that they should approach this. Okay, so, okay. And I think that, okay, so can one, of course, put it beyond polarized axis symmetry? Can one even hope to use this gauge or use this technique to understand some sort of chaotic behavior, at least to some approximation, at least some bounds? Okay? That's very much an open question. I just want to stress the difference between the predicted generic behavior and results we can prove is very large. So a method that would even try to see elements, I mean aspects of the generic behavior, even some small, not go all the way to the singularity, but some sort of dynamics. Until that happens, I think would be useful. Okay, so something.
Questions? We have plenty of time.
Can you talked about the strong cosmic symmetry thing. Can you comment on the current status?
So about black holes, right? So
Yeah.
yes. So the current status. So we've learned that it has to have the word generic in front. Okay? You can construct examples where it failed to hold, okay? But it is believed that those are non-generic. In many instances, it's been shown that non-generic. Okay? Then the most general result is this one, that a portion of the surface being weak null. So this immediately says that the strength in strong cosmic centrism is not true. Okay? You have a portion of the singularity that is null. For one-ended data, I'm not sure what the prediction is, and it depends on who you ask. What would happen to the remaining?
And whether this weak null really means inextendable.
Yes, that's the one thing where I should have prepared a little better, and I forget. So for example, if the Christoffel symbols are in L2, okay, I'm not completely sure if that's been settled. I suppose the prediction is that they will not.
So could you just say what the strongest form of it would be that hasn't been ruled out?
The strongest form
Of cosmic censorship, the strongest version of it.
Yeah, the strongest version is that generically, the metric, there's a singularity in the sense that the metric is inextendable. Right? And let's say inextendable, let's say in the Christoffel symbols on the L2. Because that would mean a weak, if it were in a, that means that you can't have a weak notion of solution with integrated mathematics. That has not been.
Is this the weak null singularity, not a curvature singularity?
I believe it is not a curvature singularity.
But that's why I said
But
that might be extendable.
No, that's the point. So you can extend the space-time, but can you also solve the Einstein equations? You can construct a metric that extends,
Right.
with a certain regularity, but does the extension solve the Einstein equation? That's
While
the key,
keeping the
right?
regularity.
So that's why a condition, I think it's actually invoking an ellipse, that the Christoffel symbol should not be in L2 is a popular choice. Because then in the sense that you need them to be in L2 to say you have a solution in the sense of integration. Okay, so,
Yes, it is associated with the mass inflection completely in something.
I don't think so. Not really. Mass inflation, does it make sense outside spherical symmetry? I'm not sure.
Yeah, I think on the Cauchy horizon, used to get some blow up of scalar waves that even in mass.
Yeah, okay. So I'm not really sure about sure.
So
Yes.
we have the Oppenheimer Schneider.
Yes.
We start with the spherical dust cloud, it just collapses.
Yes.
Makes short shade. And I think we understand how that singularity forms. If I took Oppenheimer Schneider, made ellipsoidal initial conditions, not
Yes.
sphere.
Yes.
No angular momentum. It's
Yes.
still going to be, I think, your class of solutions.
Yes.
What kind of collapse does that have? I mean, that plasma indices, for instance, will this thing get modified as I just elongate the sphere? Is
So
it
if you
one
want,
of your class of,
yes, so if you take, so I should say Oppenheimer-Snyder is not considered a good model.
yeah, Why
And it
not?
has already been shown by Christodoulou in spherical symmetry. Okay, so within spherical symmetry, it's unstable. On the ellipsoidal, I think, yeah, so you can be ellipsoidal and have polarized axial symmetry. You can do that.
Exactly, yeah. That's what I
So
was thinking.
we can throw away the matter model, okay, because zero pressure is maybe not a suitable matter model, and you can just study the vacuum pipe. So then Maribel applies. So
Okay.
nothing. So nothing.
And so you
Yeah.
can,
And so if you're ellipsoidal, but in addition have this polarization condition,
right,
you will get a space like singularity, and you'll have this scenario being a caster at each point you're approaching a different caster.
oh.
But
it
you
will
have to
really
impose
will be a
polarization.
different Kastner?
Yeah, a
So
different
the
caster at each,
indices-
yes, at each point, right? Yes, at each point, you'll be approaching a different caster
Ah,
on the final surface. So it's a rich dynamic.
oh, I thought there would just be a universal change in the Kastner index. Instead, you're saying it actually changes from,
So wait, maybe I should understand a bit better. If you perturb just the spherical cap and make it an ellipse, then by domain of dependence, you'll remain exactly Schwarzschild. If you say, I'll make it ellipsoidal, but do some sort of perturbation here,
Oh.
preserving polarized axial symmetry, my result applies.
okay,
But there's something cheap you can do, which is if you just change this cap, then at least the vacuum portion by domain of dependence will stay Schwarzschild.
We have a question online.
Okay.
Hi, can you hear me?
Yeah, I think so,
Yes.
yeah.
Yeah, I was just wondering, so, there have been these recent papers by Cardoso and Santos, et cetera, arguing that strong cosmic censorship is false in de Sitter space.
Yes.
Yeah, do you have any comments on that, or is that not evidence that maybe it's also false in flat space, or, yeah?
No, so I'm not super knowledgeable about this space. Everything I've said is about the zero cosmological setting. So I don't have a comment.
Mm-hmm.
I don't know. So.
All right, thanks.
Yeah.
Actually, that the girl side, they're okay under,
Yes.
saying that from ownership.
Even what side? Is that the law of black hole thermodynamics or something different? I think he spoke about this.
Engineered the state.
So that's spherical symmetry. So you see, well, that's part of the problem, right? So if you construct examples within a spatial symmetry class, then how automatically you're not generic in the broader set. Right? So there's that. So the strong cosmic censorship has this generic adjective in front. Okay, generic. So one can construct examples. There have been many constructions that violate it, right? But the question is how generic are they? And that's very, very difficult.
From pure curiosity, what happens if the dust is going to be charged? It's still no angular mantle, so that's really spherical symmetric.
Yes.
Will charge make any significant difference?
Yeah, I think it does. So Poisson in Israel, I think, it's not. I'm not from the vacuum, but yeah, I think Poisson and Israel have addressed that question. It does become different, but actually there is a weak null singularity there too, but I'm not sure.
So we have a quick question online. Someone is asking, what is the physical significance of space-like photon spheres?
The photon spheres on the exterior, right? So the ones that I know are in Schwarzschild are equals 3m. So that doesn't relate to this in any way. I'm talking about the interior. The physical significance of space-like photon spheres, I'm not sure what. Photon spheres are the orbits of null geodesics are equals 3m. So how can they be space? Maybe they can elaborate. Maybe that's it.
Yeah, Kumar, if you want to elaborate about that. No, I don't think it's gone.
So the ones I know are the orbits of trapped null geodesics, right? So by definition, their span, right, contains a null direction. So how can you be
Okay.
space-like? I'm sure.
Okay,
Yeah, any questions? Let's break for lunch.